to thank you and the other organizers for inviting me over here. I think it's very important that we have these focused workshops on a regular basis, and I'm informed that there are plannings to have the next workshop next year in this group again, and I think as the progress is so rapid now, I think it's very productive to have these workshops and meet everybody. So I'm going to be talking about our work on Rydberg atoms at the University of Stuttgart, and this is funded by the German Science Foundation within the SFB that we have, but also part of it is funded by the local government, Landesstiftung Baden-Württemberg. We will see at this conference or this workshop that there's a lot of progress in all kinds of branches now. Everybody, the common bracket is Rydberg atoms. So we have spectacular experiments now that we will hear about in quantum information. We have a connection to condensed matter physics. We have a connection to chemistry, physical chemistry. And I'm trying to talk about actually this stuff a little bit, about this stuff, but I would like to devote at least half of my talk, the second half, on our work on actually hot atoms, not on ultra-cold atoms, where we try to bring in the ideas that we learned from ultra-cold Rydberg work into thermal vapor cells and try to really come up with quantum devices that can actually be used later on. Okay, so when we started out working in this field, I'm coming from ultra-cold BEC type of stuff. We were interested in long-range interacting systems. We have condensed chromium, as some of you know, in order to investigate dipolar gases. In chromium, we have a magnetic dipole moment, which is giving rise to long-range interactions in quantum gases. And at some point, it was clear that these magnetic dipole moments were just too small to get really into the strongly correlated regime, and we were asking ourselves how to get larger dipole moments. And the first thought that you can have then is go for heteronuclear molecules, where you get, say, electric dipole moments on the order of, say, 1 dBi. But as you all know, the much better choice is, of course, to really think big and get the biggest dipole moments that there are in atomic physics, and that's the ones in Rydberg atoms. Now, if you combine Rydberg atoms with Bose-Einstein condensation, which is what we did a few years ago now, 2 years ago, then to estimate the potential that you have in this combination, it's good to compare the length scales that are showing up both in Rydberg atoms and in Bose-Einstein condensation. And there are 2 length scales in Rydberg atoms, one of which is the size, the Kepler radius, which is on the order of 100 nanometers. And the other one is the blockade radius. I just give one number, 5 micrometers. Some cases it's 10 micrometers. Sometimes it's smaller than that. But this is another characteristic length scale for the interaction between Rydberg atoms. In BEC, you have also length scales. For example, the mean particle spacing, giving the BEC density, typical density, is actually on the order of this Kepler radius. And there's the other length scale, which is the healing length, which is the length scale that determines all the dynamic phenomena due to the weak interaction within a condensate. And that can also be on the order of a few micrometers. And now you can just combine these length scales and try to combine them and find some new physics. So the first thing that we did was combine this length scale of blockade radius with the mean particle spacing. And you see that this length scale for the interaction is much larger than the mean particle spacing. So you are directly in this regime where you have strongly correlated phenomena that we investigated. The next topic is if you compare the Kepler radius with the mean particle spacing, you see that some ground state atoms are going to sit within the Rydberg orbit, and this gives rise to the molecules that I'm going to talk about. And there's yet another combination that needs to be explored. It's not yet done, but I think we will hear from Guido, where is he, here, about this, right? I mean, how to get some connection between the length scale, the blockade radius, to the length scale that describes the motion in quantum gases, the healing length. Okay, so I don't have to show you this slide again. I mean, this is the blockade radius picture, ground state atoms, Rydberg atoms. And the important thing to note is that this is a megahertz energy scale, whereas if you now come much closer to the typical interparticle distance in a Bose-Einstein condensate, say 200 nanometers, the energy scale of this spaghetti that you get approaches terahertz or even larger. At these distances, it's actually very hard to talk about these things anymore, right? So we really have a separation of length scales here, megahertz, micrometers versus 100 nanometers and terahertz, okay? And that actually is, I think, the secret why these experiments are actually working at all. So the first thing people were talking about this morning already is, of course, collective quantum dynamics. If you have a whole ensemble of atoms within this blockade radius, you no longer have individual states, you have collective states, and you get these superposition states, collective Rabi oscillations. And yeah, this was our first paper basically in the field. Now 2 or 3 years ago, we measured this square root of n scaling, actually for up to a few thousand atoms within this blockade radius, okay? And now there are these textbook-like experiments in Mark Zefman's group and in the Paris group, where this n is actually 2. But in our experiments a few years ago, this was a very large number, and we actually measured this scaling behavior here such that we could determine the excitation rate to scale like the square root of n in the limit of very large n here. Now, another way to express these scaling laws, okay, and this was at that time called the superatom basically. Another way to express these scaling laws is to use condensed matter language. And this is what Hans-Peter didn't talk about, and I will not talk about it very much, but Thomas Pohl was talking about it. So this is the Hamiltonian that he basically showed you. And it's the thing that you should note about this is it's a spin Hamiltonian. Yes? So it has Pauli matrices here and an interaction between spin-up components. And what you actually do here is you are mapping out a phase diagram in the space that has the detuning of the laser as a longitudinal field in terms of the spin language and the Rabi frequency as a transverse field. And you find out that you expect crystalline structures. There's a critical point here. There's a paramagnetic phase down here for negative detunings. And there is a quantum critical point here, which is actually of second order. And that's why if you do the experiment, then, you know, on resonance with finite Rabi frequencies, you get universal scaling behavior. And we measured these universal scaling laws. And actually, condensed matter physics people find this extremely interesting, because this spin Hamiltonian represents actually a novel universality class which has not been solved before. And to see this scaling behavior really work out in the lab, at least for those guys, was a major step forward. So here I summarize these results. What you see here is what a condensed matter physicist would call the order parameter. We just call it the Rydberg fraction, which goes from 1 all the way down to 10 to the minus 4 in the fully blocked regime. You see that our experimental data points as a function of the Rabi frequency in scaled units falls in this log-log plot on a straight line, which means that there is a power law behind this. We determine the critical exponent of this to be 0.45. And the nice thing is this nicely matches up with theory, both a mean field theory that was developed by Hans-Peter and also numerical calculations that were done in his group. The thing is, the numerical calculations cannot go all the way down to the large particle numbers that we have here because the Hilbert space is exploding. But the theory basically in the limit of smaller numbers gives, as a result, a very similar critical exponent. And in that sense, one can view this experiment as an emulation basically of the spin Hamiltonian in the limit of large particle numbers. Okay, so far so good. The open question in this experiment is now, is this crystalline phase really there? How can we reach it and can we detect it? And that was the main topic of Thomas Pohl's talk. Where is he? Yeah. Here. Okay, good. So we are working on that. But we also work on something else, namely we are changing the length scale now from the blockade radius, where we had about a few thousand atoms within these 5 micrometer radius, to the length scale of the Kepler radius, which is on the order of 100 nanometers. And in a BEC or close to BEC, the density is so high that every once in a while another ground state atom sits within the Rydberg wave function. And in that situation, we are talking about the interaction of this Rydberg electrons, or the Rydberg atom, with the ground state. And as it turns out, they are forming a bound state, a molecule. So if you think about these molecules, and I should mention, of course, that should have flipped those transparencies around, that we will hear about these molecules, 2 more talks, one by Chris Green, the other one by Jan Michael Rost. And they have been introduced here in this seminal paper by Chris Green, but also by Hossein and Dr. Dickinson. The nice thing about these molecules is that the binding mechanism is distinct from the mechanisms that usually are known in chemistry. So I go back to my slide here to illustrate that. If you think about a ground state atom sitting within the Kepler orbit of the electron, and you go through the numbers, what you realize is that there is a strong binding, of course, of this electron to the core due to the Coulomb force. And there's a strong interaction, or there is a binding interaction between this polarizable ground state atom and the electron. But the interaction between the ionic core and this polarizable ground state atom can actually be neglected. So you have a three-body problem, but you can only treat it by considering this interaction plus this interaction here. Okay. And as I said, this is distinctively different from the other binding types that we know in physical chemistry. Namely, it's not an ionic bond, it's not a covalent bond, it's also not a van der Waals bond. Okay. So, and in this paper here, you already see how these potentials typically look like. In this case, for a low L, in this case a 30D state, and you see that, okay, these molecules are going to be quite large in atomic units, up to 1 or 2,000. The binding energies that you should expect here are in the megahertz regime, and there are vibrational states that you can use for spectroscopy. Okay. So if you want to find them, what you do is you just do Rydberg excitation, and you just detune your laser from the atomic resonance a little bit to the red and see whether there are resonances appearing. Okay. So this is a typical spectrum here. There's an atomic line at 0 here. And then if you go to the red side, you start to see peaks here. Okay, loads of peaks. And this is for the principal quantum number 36S now. Turns out if you do a simplified model, and I'm not talking about the theory a lot because we will hear 2 more talks about this, then it turns out there's one state, namely the main peak here, which is bound by S-wave scattering of the electron from the polarizable ground state atom. Okay, and the measured binding energy of about 20 megahertz here nicely fits to what you actually expect from a very simple model, just using the scattering length as a fit parameter. But then there are all these other lines here, which I've put the question mark, which you also would like to understand. And for this, of course, you need the input of some smart theorists. And you will hear from Chris Green, but also from Jan Michael, what they actually do to provide us with these potential curves. But what you see here is, again, as a function of the internuclear distance here, 1500, 2000, the binding energy, this is the potential curve here, and then they take this curve and quantize it and get some stationary states and predict their binding energies. And you recognize this one state that is just bound by S-wave scattering here. That's the one with the red star. But you see that there are also other states that are quite different in nature. This one is just bound by S-wave scattering here. The other ones penetrate much further in. And if you look at the potential curve for shorter distances, you see that there's this dramatic drop in energy. Here the scale has changed. This is megahertz. This is gigahertz. As a function of distance, you see, you don't see this stuff here on that scale. It goes here, and then it drops down. And that's why the wave functions, basically by quantum reflection on that barrier, get reflected back and get bound by the inner turning point due to quantum reflection, and at the outer turning point by the electron density. Okay, so I would claim there is yet another type of binding here, which is different from the binding type of this one state here that basically corresponds to the simple S-wave scattering model. Okay, but we will hear more about this in Jan Michael's talk. I think it's pretty fascinating to see this. For us, this meant, okay, they have a prediction now for where these other states should be, and we compared them with the experiment, and here are the theoretical predictions, and you see that there are some things missing. I mean, some of them are actually lined up pretty nicely, but there are some places where there was no signal. So we went back to the lab and looked a little bit more careful onto our MCP signal that we get after field ionization. Whoops. And if you look closely, then you see that we not only get a signal after field ionization at rubidium plus, but also a little bit later, due to the larger mass, at rubidium 2 plus. And if you just plot now the rubidium 2 plus signal as the function of frequency at the same time as we plot the rubidium plus signal, you see that in this spectrum, some additional features, like here, for example, show up that we could not identify, at least in the upper graph. And you see also that there are now, again, new things showing up. For example, this line here, which has no corresponding line in the theory. Okay. What you can also learn from this is that actually one of these peaks, the outermost one, is a trimer peak, which actually has exactly twice the binding energy than this and this S-wave bound vibrational ground state. And we have more data on that. You see that we have found these trimers for a whole bunch of different principal quantum numbers. So this is actually three-body photo association, if you like, because we do this by two-color photo excitation, which, at least according to the discussion that I had with Paul Julien, has in other systems has never been done. So we have trimer lines, a whole bunch of dimer lines, and I think there's a lot of physics coming up now that we can discuss here. I want to focus, as advertised in the title here, on the ability to do coherent control experiments with these molecules. What do I mean by this? I mean that I can manipulate or excite basically the atoms in a coherent way into this molecular state. So I can think about a superposition state of free atoms and bound atoms. Now, in the field of cold atoms, that's not a very new situation. This actually came up when the Feshbach molecules were fashionable, like 7-8 years ago. There was this famous experiment at Gila, where they were pulsing Feshbach molecules on by magnetic field pulses here, and basically were showing that it is possible to have a coherent superposition state of Feshbach molecules, which are actually similar in size, right? These are these very weakly bound, fluffy molecules. And you can make a superposition of those Feshbach molecules with free state atoms. And they were basically using a Ramsey technique to demonstrate that. Now we can do something similar here. We don't use a pulse echo technique. We use what is called a rotary echo. And I just briefly explain to you what I mean by that. But basically, this rotary echo also demonstrates that we have a coherent superposition of free and bound states in the end. Okay. So what is it about? A rotary echo basically is a well-known technique in NMR. You start with a Bloch vector pointing downwards. You apply a pulse for a certain length. Then the Bloch vector moves up here. And at some point, you change the phase of the driving laser by pi. So that means in the Bloch sphere, your Rabi frequency vector that was pointing along you now points against you, so it flips the sign. And that means that the excitation that you have been doing is just getting undone. Okay? And this works perfectly if this phase flip happens right in the center of your excitation pulse. If you do it too early, well, then there will be some excitation left. If you do it too late, then there will be also some excitation left. Okay. So now what we do in the experiment is we keep a fixed pulse length and we just vary this time where we actually flip the phase. And then we get an echo curve, a rotary echo curve, which we can use to measure things like visibilities and dephasing times and so on. So the typical echo curves that we get on the atomic lines look like this. So this is a pulse that has a length of about 500 nanometers. Actually, that's the PhD thesis of Ulrich, who's sitting in the back here. And you see that if you flip the phase right in the center of this pulse, you get a minimum signal. Okay, it's not going all the way down to 0, so there's a finite visibility due to some dephasing mechanisms. But you see that these echo signals basically have a finite and clearly clearly quantizable visibility that you can use for further like dephasing time measurements. Okay. Now we can, okay, yeah, I should skip that. We can do this on the atomic line. This is a signal now that we get for 700 nanosecond pulse length. But we can just as well do the same thing on the molecular line, of course. And without changing any parameters, you immediately see that on the molecular line, the visibility is actually larger. It's actually better. Yes? And the reason for that is, of course, that the dephasing mechanism in the dense sample on the atomic line is the Rydberg-Rydberg interaction. Okay. Now, as we excite molecules, the effective density of Rydberg atoms goes down, and therefore the dephasing due to the Rydberg-Rydberg interaction, in this case Rydberg molecule interaction, is much less, and therefore the visibility of this pulse echo signal goes up. So we can use this and measure dephasing times, and the dephasing time that we have determined in our system is on the order of 1 microsecond. So we have 1 microsecond basically time to do coherent physics with these molecules. Okay. So to conclude this first part about Rydberg chemistry and give some outlook, we just observed actually, I think, 2 novel binding mechanisms for dimers and trimers here. There's a very good agreement with theory. I didn't talk about decay and reaction channels, but this is also a new aspect here, and we are able to control those molecules in a coherent way. Now, next steps could be to really look for permanent electric dipole moments, like in these high L states in the trilobites. I mean, that was one of the very peculiar things about these molecules in the early days. I mean, this is a homonuclear molecule, but it has a permanent electric dipole moment as indicated by this wave function here. So it would be very nice to see this actually in the experiment. We would like to go to higher L. So far, these molecules are S-state molecules. So the nice trilobite shape where you see all the nodes in the radial part of the wave function would be nice to investigate. We have coherence times of 1 microsecond, and that means if you compare it to the vibrational frequency, we have some time to do actually wave packet dynamics in these vibrational degrees of freedom. And then, of course, there are very nice ideas to even look for trimer states in the situation where dimers do not bind, so-called Borromean trimers. That is going back to work that was also done in Dresden. And there are many more things, and I'm happy to discuss with you all what else one could do here. But I would like to switch gears and come to the second part of my talk, as promised, and really pick up on this idea of the Rydberg blockade and these collective states and the superatoms. So I was saying that, okay, if we have a blockade radius that is larger than the size of the ensemble, then we get all these nice collective states, and we could use this ensemble as a mesoscopic ensemble to do quantum information processing. There are many proposals out there. And I'm now taking a figure that was produced by Charles Adams here and ask the provocative question, do we really need a BEC or ultra-cold atoms to do this kind of physics, or would it be possible to do this in thermal vapor cells? So why not use dense hot atoms instead of an ultra-cold sample. And if you think about it, what you really need for this is a frozen gas that is dense, so many particles within the blockade radius. And if you just look at the vapor pressure curve, then at around 200 degrees, the density that you get in a normal vapor cell is as large as in a Bose-Einstein condensate, or even larger. Okay? Or in other words, the mean atomic spacing is similar or the same as in a condensate, right? So at these temperatures, within a blockade radius, you can get 1,000 atoms and get a collective coherent evolution, in principle. Okay. Now there are lots of problems, of course, but we said, okay, let's really take this a little bit more serious and ask ourselves, what is this system like? Think about this Rydberg atom that is producing a blockade radius that is sort of blocking any further excitation outside this, say, 5 micrometers, as we said. Okay? And now let's build a container around this thermal vapor cell that is smaller than the blockade radius. So this means, think of a thermal microcell that is really micrometer in dimensions. Put a thermal vapor into a bubble of glass, say, that has a diameter of a few micrometers. Okay? Then I would expect that it's only possible to have a single Rydberg excitation within this volume. And this vapor cell would actually do the same thing that we all discuss now with in the context of cold atoms. Namely, we could use it as a single photon source, as was discussed by Thad, where is he? Here. With all the nice features, right? Directed emission, so due to 4-wave mixing and so on. It's, of course, operating at room temperature. If you coat this cell, the nuclear spin can actually survive up to 10,000 collisions with the wall. So the nuclear coherence times can be pretty large. As the length scale is micrometer, photolithography can be applied. It's not really a big deal to produce those cells with micrometer dimensions. And of course, they can be easily positioned, like in a linear chain, for example, or lattice, if you like. And the competing system to all of this is, of course, not ultra-cold atoms, but quantum dots, right? If people work in this field of quantum dots, what they do is very similar. They have a 10 nanometer large object. There are about 10,000 valence electrons. They excite one of these valence electrons into a collective exciton state, and they let it decay and get a single photon out. Now, as this quantum dot is much smaller than the wavelength, the single photon emission is radiated in all the 4 pi angle, right? So it's not a directed single photon source. There's already one advantage, basically, of doing this if you compare it to quantum dots. Of course, they typically work at low temperature and not at 100 or 200 C, right? So that's another advantage that makes this sort of interesting for applications. Nuclear spins is a problem here, typically, right? They give rise to dephasing and uncontrolled states. We can just do optical pumping and control the nuclear spin. Spin coherence times are, for that reason, shorter. Growing those quantum dots and especially positioning them in a lattice is a tricky problem. And there are many people working on this, trying to really get quantum dots next to each other on the 10 nanometer scale, right? Because their size is so small and their coupling length scale is a few hundred nanometers. You really have to position them with a 10 nanometer resolution. So it's really challenging for lithography and so on. So I think lots of reasons why we should try to do this, although it's crazy, right? Let's see how far we get. So these are artificial atoms, and I'm claiming that what we do here are artificial quantum dots or artificial atoms, right? We should know that artificial is not the inverse of each other, right? An artificial atom is not an atom, it's a superatom, right? It's a collective state. Okay, so the work plan, take a thermal vapor cell, and that goes back to the work that will be discussed also by Charles. They showed us how to do Rydberg EIT in a thermal vapor cell already some years ago. So in 3 dimensions, without any boundary, this was done. So in this talk, we are going to do the steps that people in semiconductor physics did many years ago. So we go from 3D to 2D, where we have quantum wells. So this means we make a cell that is actually thinner than the blockade radius. And then we go one step further. We make a cell that in 2 dimensions is smaller than the blockade radius. That's a quantum wire. And we go one step further and really confine it in all 3 directions. Then we have a quantum dot. So that's the work plan. We are not quite there yet, but we have some results here and there, and I would like to talk to you about this. Huh? 2 minutes, my God. So there are lots of interactions here with the walls. That's, of course, the main thing here. The Rydberg atom can interact with its image. It can interact with charges. It can interact with surface polaritons. And I should make this shorter. There are lots of surprises here. The main thing is, the main interaction is surface polaritons. And if you choose the right state, that's the real interesting result now. If you choose the right Rydberg state, which is 32S, you can watch this EIT peak all the way down to 1 micrometer thickness of these vapor cells without a significant shift and a significant broadening. Okay, so the width of this peak is on the order of 20 megahertz, and that's just given by collisional broadening. We see more or less the same width at 70 micrometer and at 1 micrometer. Now I skipped the secret about this because I had no time, but the secret is that this state avoids any coupling to resonant surface polariton in the quartz walls that we are using. Okay? If you take any other state or other states that have a stronger coupling, then you cannot follow this EIT signal here. Then you get broadening already at the 10 micrometer level or before, right? So but I think now there is a way to coherently excite, this is an EIT signal, to coherently excite Rydberg atoms in a 2D configuration where the confinement due to the quartz walls is smaller than the blockade radius. So let's move one step further. Okay, so this is, let's move one step further. So we have shown that Rydberg atoms can be coherently excited in a 1 micrometer cell. Just think about it, right? The Rydberg atom is 100 nanometers in size, and the wall is, the distance between the 2 walls is just 10 times that, right? And we have taken one more step to make cells that actually are 1D. Okay, so what do I mean by that? This is a cell that we made, which is fed by rubidium. You see rubidium in the metallic state here, so it's diffusing in and up here, and then it diffuses all the way out in this little tube. What is this tube? Well, it's etched, it's a groove basically etched into glass, and the rubidium is just diffusing in here. So we have channels available that are filled with rubidium, and the dimensions are again on the order of the blockade radius. I mean, the thickness is 1 micrometer, width is 10 micrometer. That's the current status right now, okay? And we can get rubidium in there. Oh, so you can't really see this, but there is a normal saturation spectrum taken right at this position in a confocal microscopy setup. And with this confocal microscope, we can do something that the quantum optics people also do. They excite at some wavelengths and detect at the other wavelength, which is in the rubidium just the blue fluorescence line, and they detect this in the spectrometer. Okay. So we have just a microscope objective, these 2 lasers to excite our rubidium here, and that's one way to check, well, do we have rubidium, and what is happening with this rubidium, for example, due to the presence of these walls. Okay, and here is some signal as a function of the position over a channel. In this case, it was 40 to 20 micrometers wide. We see the fluorescence on the blue line. We see the absorption here. So this is just confirming basically that we are successfully loading rubidium atoms into these channels. And then we can do something more. We can even look at the ratio of certain lines and detect spin flip processes that are induced at the surface of the confining walls. Perspectives for this is, of course, quantum information processing. So just consider again that we have these glass cells, and the dimension of this is 1 micrometer. Then if there's a Rydberg atom excited here, the neighboring cells cannot be excited, and that's the crucial ingredient that you need for 2 qubit quantum gates, just like you do it now with cold atoms separated by optical tweezers. Okay, this brings me to the end. I would like to thank the people that have been doing all of this. There's a team working on cold atoms, which is led by Robert, but we had a strong input, of course, from Hans-Peter and Hendrik here. The molecule work is Vera's PhD thesis, and Björn and Johannes are also members here. You will hear more about the molecule theory in Jan Michael's talk. This is the microcell team. Again, Robert is involved here. Jim was very important. He spent a full year of his sabbatical with us working on this, and that's basically the PhD thesis of Harald Kübler. Thank you for your attention.
So thank you for this very nice talk, great results. Let me ask the first question. So what's the secret to choosing the right state there?
Thank you. Well, okay, yeah. So that's the secret, right? I mean, we started out with our regular state that we usually take, the 43S state, okay? And we narrowed down the gap in the cell, and we saw, okay, well, this is a huge shift, 400 or 500 megahertz shift of the line due to the presence of these walls at about 20 micrometers. And you see the same thing if you heat up the cell. So you see that there's a shift and a broadening on the frequency in the frequency range of 500 megahertz. So huge effects. But then the surprise came when we did the same thing on the D state, okay? Then we saw that some of the lines are shifting and broadening, like in the S state, but there is this line here which is not shifting at all, and it's also not broadening, so there's a dark state. So there must be something going on that is polarization sensitive. And what is polarization sensitive about Rydberg surface interaction? That is the interaction with surface polaritons. And this has been, for example, studied in, not for Rydberg atoms, but for cesium atoms, much lower lying states in the Ducroix group. Now, if you have surface polaritons, then they can take your state and couple them to other states, right? And so there's a chance for the Rydberg excitation to get dumped into the surface, because the surface has very broad resonances that act as a reservoir, and you just throw all the Rydberg energy into this reservoir. Okay. Now, if you look into the literature, then these polaritons have a very nice and discrete structure. They are known. I mean, here are the resonance frequencies. So the surface has a fingerprint in frequency space. The Rydberg atom has a fingerprint in frequency space, and you just have to choose the right state to avoid any overlap between the two, right? So that's what this figure should show you. The 43S state has an overlap here, there. So lots of possibilities to dump the energy into the surface. But if you take the 32S state, then you avoid this resonance, and the overlap of the two fingerprints basically is minimized. And if you follow this rule, then you find the right state, and you also see in the experiment then that there's no coupling due to surface polaritons left in the system. Okay, that's the secret. So now, as we understand that, of course, we can think the other way around. Let's take a material, not quartz now, right, for these cells, that has another polariton spectrum, right? If we like to work with much higher principal quantum numbers, again, to get larger blockade radius, then we should just get rid of these polaritons. And there are much harder materials that have polariton frequencies that are actually much harder. Yes. My favorite is diamond right now. So.
So for these microcells for qubit applications, one thing you didn't touch on was when the atoms are hot, they're moving 10 to the 4 times faster, you have a dephasing issue. Any comment about that?
Sure, yeah. The comment is you have to be fast, right? So it's not a microsecond pulse, it's a nanosecond pulse. So we're glad that we had Jim working with us, because he set an amplifier up for us that is amplifying the 480 nanometer light in a nanosecond pulse that is bandwidth limited, that we can then use to do coherent Rydberg excitation on a nanosecond time scale instead of on the microsecond time scale. That's a crucial point, and we have to.
But then if you want blockade, you have to have corresponding.
Yes, but it's completely true. Instead of megahertz, you have gigahertz now as a bandwidth of the pulse. But the van der Waals interaction, for example, just goes with the 6th power of this. So this reduces your blockade radius by a factor of 3, but that's not dramatic. It's not really a showstopper here. Yeah. It's a smaller blockade radius, but just by a factor of 3.
How many wall collisions does the Rydberg atom make in a coherence time?
The line width of this EIT signal that you saw here, the 20 megahertz, is limited by that, by the collisions with the ground state atoms and also by the Rabi frequency. So that's about this 20 megahertz line width that you get just due to that, right? But that's plenty, if you think about 1 nanosecond pulse of a coherent evolution later on, on that time scale, the collisions of the Rydberg atom with the wall don't play a role anymore.
From that perspective, why have a wall? What does the wall actually do for you?
Well, at least in one, you can talk about the transverse directions, but at least in this direction, it helps you to address the volume that you want to talk to, right? If you want to make a single photon source, for example, you really want to be sure that you are only exciting one Rydberg atom. Now, you can say, okay, let's just focus the laser down, and then radially, I agree with you, you will get a spot in our confocal microscope that is smaller than the blockade radius. But in the 3rd dimension, you don't. So at least for that, you need the confinement in one direction for the single photon source. If you want to work with the nuclear spin, though, you want to really store the information in the nuclear spin, then you want to keep this ensemble localized and let the ground state atoms collide with the wall and keep the spin polarization. That way you get 10,000 times longer coherence times for the nuclear spin than for the electron spin.
One short question, please, and a short answer, please.
So it's perhaps technical, but do you see any effects of aging? I would expect that maybe as the surfaces get coated, those resonances broaden out, and you don't.
That's a very good question, and we worked a long time on that. If you use the right materials, you can avoid it. We can talk about these little secrets.
Okay, thanks again
Okay.
for this exciting talk. And